Dinosaurs. Massive reptilians that once ruled the Earth for millions of years are now just some fossilized bones and the source of oil to power my car. Scientists say an asteroid wiped them out 66 million years ago, but what if they could jump? Maybe, just maybe, they could have jumped over the asteroid's shockwave and survived. The first step in my grand plan required me to create a clone of the famous Chrome dinosaur. I normally use Java to code, but during all my research, one word kept showing up. Now, one good thing I learned about Python is that there are a lot of resources on its library Pygame. So using Pygame and some online tutorials, I was able to develop this almost exact replica of the real game. Now it's time to teach the dinosaurs how to jump. To teach a dinosaur how to jump, I have to first develop an AI. Now, there are many pathways I could take to develop this AI, but I recently learned about the NEAT algorithm, and so I'll use that. The neuroevolution of augmenting topologies, also referred to as NEAT, is an evolutionary algorithm which was created by Kenneth O. Stanley for evolving neural networks. Now, without getting into the nitty-gritty, I'll explain how NEAT works in simple terms. Generation 1 is evaluated on how well it does its tasks, based on something called fitness. There are many different ways to calculate the fitness, but in this example, the fitness will equal how long a dinosaur survives. Then it takes the best of that generation and passes on its traits to the next generation with reproduction. This new generation then employs crossover and random mutations to vary the behavior of each individual, and it keeps going until they figure out a solution. And this was my first try. I spent literal hours trying to debug this monstrosity, but I just could not figure it out and decided to just remove the ducking feature for the AI. My first NEAT algorithm resulted with a max average score of 1000, but I knew that it could be stronger. The first set of tests I did was testing out the most optimal size of population that I should use to effectively train the AI. If you have a small population, like 5 or 10, then instead of growing, they continue doing the same thing every generation because of a lacking gene pool. On the contrary, large populations of 75 and 100 had their own problems. While one would expect that the bigger the population, the better, the large populations often resulted in stagnation during the middle generations and also took a significant amount of time to train. 50 wasn't the Goldilocks zone. It generated the best results out of all the samples, showed minimal signs of stagnation, and also had the most profound peak performances out of all the trials. Now that I had my population size down, it was time to refine the code of the AI. The first thing I added was a penalty for continuously jumping. As you could see, in the first few generations, some dinosaurs would keep jumping and by pure luck end up farther than the rest. By penalizing continuous jumps, it forces the AI to run for the majority of the time and only jump when it is really needed. Then I tested on different data points which would be inputted into the AI. Right now, the AI only was fed the y distance of the dino relative to the ground, and the distance between the dinosaur and the middle top of the next obstacle. I tried inputting all kinds of data, like the top left and top right of the obstacle, the type of obstacles, the amount of obstacles coming in, but nothing worked. Then, while rewatching footage of previous experiments, I came across a breakthrough. Now, if you played the game before, You know that the farther you progress, the faster the game gets, and the quicker you had to anticipate your jump. But the AI never knows that, and once I added game speed to the AI as an input, it broke all my expectations.